Delta V, often stylized as delta V, is a fundamental concept in astrodynamics and space exploration. It represents the change in velocity needed to perform specific maneuvers in space, such as reaching orbit, landing on another planet, or adjusting a spacecraft's trajectory. This article explores what delta V is, why it matters, and how it shapes space missions. Delta V is a scalar quantity measured in meters per second or kilometers per second that quantifies the change in a spacecraft's velocity required to achieve a particular objective. The term delta comes from the Greek letter delta, meaning change, and V stands for velocity. In essence, delta V is the push a spacecraft needs to alter its path or speed in the vacuum of space, where there's no air resistance or friction to contend with. Delta V is not just about speeding up or slowing down, it encompasses any change in velocity, whether in magnitude or direction. For example, a spacecraft may need delta V to escape Earth's gravity and reach orbit. It might also need delta V to transition from one orbit to another, like moving from low Earth orbit to geostationary orbit. During interplanetary travel, a spacecraft may perform a course correction, which requires delta V as well. And of course, landing on or taking off from a celestial body like the Moon or Mars also demands a certain amount of delta V. Delta V is a critical metric in mission planning because it determines how much propellant a spacecraft needs. The more delta V required, the more fuel the spacecraft must carry, which, increases its mass and cost. Since rockets have limited fuel capacity, engineers must carefully calculate the total delta V budget for a mission to make sure the spacecraft can complete all planned maneuvers. The importance of delta V stems from the Tsiolkovsky rocket equation, which relates a rocket's delta V to its propellant mass and engine efficiency. Okay, so the equation is delta V equals exhaust velocity times the natural logarithm of the initial mass divided by the final mass. In this equation, delta V is measured in meters per second, exhaust velocity is also in meters per second, initial mass is the mass of the spacecraft including all its propellant, and final mass is what's left after all the propellant has been used up. And, just to clarify, the natural logarithm is what we use for the calculation here. This equation shows that delta V depends on the efficiency of the rocket engine, which we measure by its exhaust velocity, and also on the ratio of the initial to final mass. So, a higher mass ratio or a more efficient engine will allow for a greater delta V. Different space missions, require different amounts of delta V depending on what they're trying to accomplish. For example, here are some typical delta V values for common maneuvers. To reach low Earth orbit, which is about 200 kilometers in altitude, a rocket needs about 9.4 kilometers per second of delta V starting from Earth's surface, and that includes the effects of atmospheric drag and gravity losses. So, transferring from low Earth orbit to geostationary orbit requires an additional delta V of about 4.3 kilometers per second. And, to leave Earth's gravitational influence entirely, a spacecraft needs roughly 11.2 kilometers per second from the surface, or about 3.2 kilometers per second if you're already in low Earth orbit. A round trip to land on the Moon and return calls for a total delta V of around 15 kilometers per second, and that covers orbit insertion, landing and takeoff. On the other hand, a one-way trip to Mars, including orbit insertion, typically demands about 5 to 6 kilometers per second from low Earth orbit, with more delta V needed for landing or a return journey. Now these values are approximate and can vary, depending on things like launch location, trajectory, and whether gravitational assists are used. There are actually several factors that influence the delta V required for a mission. For example, escaping the gravitational pull of a planet or moon, what's called a gravity well, requires a significant amount of delta V. Larger bodies with stronger gravity demand more delta V than smaller ones, and when it comes to atmospheric drag for launches from Earth, rockets lose some delta V to air resistance, which, increases the total delta V needed. Trajectory optimization is also key. Efficient paths like home and transfer orbits minimize delta V by leveraging orbital mechanics. Gravitational assists, involve passing close to a planet to provide what's basically free delta V by using the planet's gravity to alter the spacecraft's velocity. Staging, on the other hand, is when multi-stage rockets shed empty fuel tanks to reduce mass, which increases the effective delta V per unit of propellant. Spacecraft designers actually use delta V maps to plan missions. These maps show the delta V required to travel between orbits or celestial bodies, helping engineers select the most efficient routes. For example, a delta V map might reveal that a direct trip to Mars requires more delta V than a route that includes a Venus flyby for a gravitational assist. Delta V also influences spacecraft design. A mission with high delta V requirements may use advanced propulsion systems such as ion thrusters, which provide high exhaust velocity but low thrust, or chemical rockets for high thrust maneuvers. Alternatively, mission planners might incorporate technologies like aerobraking to reduce delta V needs. Delta V is honestly the currency of space travel, dictating how far a spacecraft can go and what it can achieve. By understanding and optimizing delta V, engineers design missions that push the boundaries of exploration, from orbiting Earth to landing on distant worlds. Whether it's calculating the fuel needed to reach Mars or adjusting a satellite's orbit, delta V is the key to navigating the vastness of space.